Okay, let's take a look at this problem. It's number 10 from 4.4 for Calculus 2. So populations that can be modeled by the modified logistics equations dp dt equals p times b times p minus a. Now, of course, p is the population, t is time. Can either trend towards extinction or exhibit unbounded growth in finite time, depending on the initial population size. So if b is 0.005 and a is 0.44, use phase portrait analysis. And so I just I came up with some equations and graphed it with Desmos to see what was going on. And I really feel like this is throwing something in there that's not in the book, and I can't seem to find any other reference to it. So if you look at your slope fields, that might be a way to interpret it, to see where the trend is going, but you can also graph the two different populations that you put into it. But that's really, there's a lot of work we need to do to get to that point, unless there's something that I'm not seeing in doing the problem. So just to start off, what we were used to seeing is dp dt equals rp times 1 minus p over k. So when I see a formula like this, where I have my dp dt equals p times b is 0.005 times p minus a, which is 0.44, I'm going to try to make it look like this because I know how to set that up into an equation. And if we play with this a little bit, so here's my thing. If you know a shorter way of doing this, maybe I'm making things much more complicated than I need to, but we do that sometimes. So I need some space to work. I'm going to come on down here and rewrite things a little bit. Give myself some more working space there. Okay, because I got a couple pages of notes here on paper. So I have my dp dt equals p times the 0.005 times p minus 0.44. And I want to factor out the 0.44. So when I do that, my dp dt becomes, and I factor out a negative 0.44, so it fits in the model, the model being dp dt equals rp times 1 minus p over k. Notice the p part is being subtracted. So in this case, the p part's not being subtracted, so I have to factor out negative 0.44, and then I end up with 1 minus p over 88. So you can just double check that. If you did 0.44 divided by 0.005, you get your 88. And so now our formula is starting to look like the standard formula and the solution here. And I'm not going to go through the whole derivation because they already derived the solution for us. So P of t is the initial population, P sub 0, times our 88, e to the negative 0.44, because that's our r. That's the r. The k is the 88. Times t over 88 minus p sub 0 plus p sub 0 e to the negative 0.44t. And what I'm referencing is in the book, the online book, if you look at, it really doesn't have pages, but I'm on 4.4. The formula they give us for, it's theorem 4.2. And we're looking at P of t equals P sub 0 times k e to the rt over k minus P sub 0 plus P sub 0 e to the rt. Okay, so now that I have this, I need to do a little bit of manipulating, and let's work with this a bit. Now, the general solution to these is P equals m, which is our carrying capacity over 1 plus a e to the negative RT. So now we're going to look at a specific situation. So they give us two values to work with, and we have P sub 0 is 163, and P sub 0, let me go back up here, being 28. We got these two to look at. If we talk about the equilibrium of this, and what I want to get at with the equilibrium is that's where our dp dt equals 0. So that is, the change is going to be a 0. That's equilibrium. So our dp dt equals 0 whenever negative 0.44 times 1 minus p over 88 equals 0. So I hope it's pretty clear to see if you set p equal to 88, then you'd have negative 0.44 times 1 minus 1 equals 0. So 0 equals 0. So, I mean, so 88 is the carrying capacity, is the equilibrium. So that's what this answer here is, 88. Now, given that, we talk about when the population tends towards extinction and when it's going to grow without bound. So this person already did this part and they got it correct. So it's going to grow without bound if our population is 163, and that's above the 88. It's going to go extinct if it's below the 88. So, and you can plug those numbers in too in the final thing. But what I want to get at then, just focusing on the 163 portion. P sub 0, our initial population is 163. That makes P of t equal to 163 times 88 e to the negative 0.44 t over 88 minus the 163 plus 163 e to the negative 0.44 t. And this gives us, let me go ahead and continue on here. So 163 times 88 is 14,344. 344 times e to the negative 0.44 t divided by the 88 minus 163 is negative 75 plus 163 e to the negative 0.44 t. Now, because I want to have this model here, the way I approached it is I multiplied on top and bottom by e to the negative just e to the 0.44. E to the 0.44 t to cancel out it there. And that's going to go across those terms. So we end up with our P of t being 14344 divided by, so this 163 e to the negative 0.44 t gets multiplied by e to the 0.44 t, so that cancels. We're left with 163, and then we have minus, because the 75 minus 75, and that gets the e to the 0.44 t. And so this gets us into this formula now. And so the question is, oops, scrolled up, sorry about that. The next part, so it's to solve modified logistic equation, A and B, and give an initial value population. So that's this formula here. Now the answer they had divided this down. This is equivalent to it, but they had divided that down a little bit. And I'm not sure why, but they divided top and bottom by 200, so multiplied by 1 over 200. And then that gave them the result of 71.72 over 0.815 minus 0.375 e to the 0.44t. And that's the answer they had. The last part of this question is to ask the time that you're going to hit, or as t goes to infinity, what would this population be? Or find the time such that p of t goes to infinity. That's what it is. So we're looking at, so when is this going to increase without bound? It increases without bound when the denominator, this 163 minus 75 e to the 0.44t, is 0. So that's where 163 equals 75 e to the 0.44t, or 163 divided by 75 equals e to the 0.44t. Then we take natural log of 163 over 75 equals natural log of e to the 0.44t. That cancels. So natural log of 163 over 75 equals 0.44t. Divide by 0.44t, which is 44, excuse me. And t would equal 1.76423. And that's the time that it increases essentially to infinity. So not very long. So 1.7, let me just put it up here. And our formula was 71.72. Again, it's equivalent to what I had, but this is how they have the answer. And they divided everything by 200 each of these terms. 0.815 minus 0.375 e to the 0.44t. So kind of messy there. Sorry, took a little longer too. Hope that helps.